Okay. If you didn't get your test back, I'll get those to you when we finish up today. So I do have we passed them back Tuesday, right? So if you missed that, we'll be there. What is probability? How do we calculate a probability? There's two steps. Very good. So that's the second step. How do you get the results? So what's that? You could do a survey, but what about the survey do you need to do? You need to good. You need to count, right? You need to count the results, the events. You also need to count this what we call the sample space, and remember that's a little different than what we were talking about samples before being coming from a population. The sample space is everything that could potentially happen, right? So we have that, and then as you stated, it's the number of events that we're looking at, specific events like is it raining, divided by everything that could happen, which is not raining or raining. Okay. And if you looked at the weather app this morning, you saw about 100% chance of rain because it was raining pretty bad, at least where I was at. Okay, so what we're doing today is we're going on with that, but we're going to finish up a little bit here with the 3.1. 3.2 is what's called conditional probability, which means we know something had already happened, and so that kind of changes the way we count. And if we change the way we count, then we get the right answer. So we take that additional piece of information we have, like it's already raining, and then now we might think of what's your chances of getting in, say, a car, hopefully just a fender bender, but having a car accident. Do you think it'll be higher when it's raining than when it's not raining? From your experience, probably, yeah. Every time I've been in an accident, it's been raining. So I'm real careful in the rain because it's scary. All right. So let's go with this one. Now we did yesterday this one concept sort of at the end. If we had say a 70% chance of rain, what would be the chance of it not raining? 30%. You took the 100% minus the 70%. So everything happening has to be 100%, and we just subtract. So that's what this next one's going to be about. We did a similar activity with this one earlier in the lesson. Well, this one doesn't give me my pin when I want it. Go with red. So in this case, find the probability of randomly selecting a social networking site user who is not 25 to 34 years old. So we calculated that they are 25 to 34 years old. So how would we go about doing this one? Got the ages along here. Very good. So the total or the total probabilities, right, is always going to be 100% or 1 if you're working with decimals. So we could think of it's going to be 1 minus 765 divided by 3,000. What could be the other way to do this? That might be a little bit more work. You could actually add all of these together, right? You're directly finding all the ones that are not in that group, but that's more work, right? So it can be done that way, but what you're going to find out, and I remember when I was taking my probability classes, I wouldn't spot the easy way first, and I'd start doing a lot of work, and I go, wait, there must be an easier way. And then at the end, I said, oh, just subtract from 1. Fine, so You don't always spot it, but yes, this one would be it. And so we're going to get, I think this one was 2.255. And someone might, and you should have your calculators out because we want you sort of active through these next ones to see how you do it. So check me on that 765 over 3. I'm just going off of memory. I didn't actually calculate it in my head because I can't do that. And then when we subtract, that's, I think, 74.5%, so 0.745. So again, that's an important technique we use whenever you see the not. But again, sometimes you miss that not part because it's just a little thing. But if you can spot it, oftentimes, it's kind of like don't follow their instructions, switch it over. You could. Okay. So far, so good? So again, it's really, we just have to count, but we have to be careful what we're counting. And then sometimes with probability, we have an easier way to calculate. We calculate what we don't want and subtract it from 1. Then we get what we do want. Okay. This one is we're gonna use tree diagrams for our counting to kind of see how it goes. So for this one, we have a probability experiment. We're going to toss a coin. And if you toss a coin, what are the outcomes? 2 outcomes, heads or tails, right? And then we're going to spin a spinner. And it does tell us that the spinner is set up so it's equally likely to land on any of the numbers. Notice the numbers are kind of are mixed up around here. It's not going straight through there, but how many different numbers could we possibly get there? So 1 through 8, even though it's not right. And so event A is tossing a tail and spinning an odd number. So I'm going to go to the next slide, which has the tree diagram set up. And this is what I was meaning before when I talked about tree diagrams. Sometimes they would be, to actually draw this thing out, mine would be very messy. I don't know if it'd be helpful. But let's count. Tossing a tail and spinning an odd number. So we come down heads or tails. Which one are we looking for? And actually, they're missing a D there. There should be and. So we've got a tails and then getting an odd number and getting an odd number. And means both those have to happen. So how many odd numbers are there here? There's 4 odd numbers. How many total things could happen? You'd have to count all of these. So there's 8 here and 8 here. Gives us a total of, sample space is 16. 4 of these are things would constitute event A. So our probability is 1/4, 25%, 0.25. So all 3 ways of writing it are correct. So far, so good. We're going to look at the, on Tuesday, we get to something with the OR probabilities, and I think the AND as well, but we're going to do it just with counting. So this is a little different. It's tossing a head or spinning a number greater than 3, or. So if we get a heads, which one of these have heads? Don't all of these? So this would qualify, even we're not looking for, so these all qualify as having a heads. But then we have this or spinning a number greater than 3. Well, we've kind of already taken care of here. On this side, what numbers are greater than 3? 4, 5, 6. So I save ourselves some time and just go this way. 1, 2, 3, 4, 5. 5 plus 8. So we could think of it as 8 out of 16 plus 5 out of 16. giving us 13 out of 16. Is that right? Yeah, 13 out of 16. So again, just being careful how we count it. So we're also going to look at OR probabilities, maybe with larger numbers, and there's actually a formula you can use to do that. But yeah, okay. So again, just counting, and sometimes counting means you have to draw a picture to see what's going out, to what, that you're counting the right items. Okay. And now this last one is going to lead us to something. We did some with getting codes, right? A 4-digit code. So this one, we have an 8-digit student ID number. So each digit can be 0 through 9, and each digit can be repeated. So what you want to kind of, the way I go about this is there's going to be 8 digits, so I put 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. And then we count for each of those 8 digits what we could possibly put there. And so if we can use the digits 0 through 9, how many do we have for the first digit? There's 10, remember? So that's 1 through 9 is 9, but that 0 gives us a 10th thing. And then since we can repeat, they're all going to be 10s, right? So we could see, okay, this is one with repeating. We really just get 10 to the 8th power because we're going to do 10 multiplied 8 times, which is 1 with 8 zeros behind it. It's pretty big. What's the probability of getting your college identification number? So how many college identification numbers would you have? You have one for Reedley, right? You only have one number. Everyone has one number. So the probability that your number is picked and you get the $1 million prize. You didn't know there was a $1 million prize in this? No. I wish, right? Is going to be 1 out of 10 to the 8th. See, 1, that's 2, 3, 4, 5, 6, 7, 8. See what that number is. There's 3. That's 100 billion, 1 in 100 billion chance. Okay. Now the reality is probably not all those numbers have been used. So if it's just, some kind of a lottery where all the student numbers are thrown in there, then your chances of winning would actually be better than that. But if all the digits were used and it was just randomly done that way, the only way to match, you're only going to have one match, right? All the digits have to match. Make sense? Okay, so probability, counting, and then a division. How many are in the event divided by the total sample space, how many things are possible. What I want to show you is we'll be getting to some of this in the homework. Is one way of counting involves what we've been doing before, something called a permutation and a combination. And I'm going to, there's formulas for each of these, but what I'm going to show you is just how to use the calculator to do it and explain what it is. A permutation, we've got some items that are going to be put in an arrangement, and this is where the order of how they were chosen is important. So there's a first, second, third place. Or we're putting books on the shelf, and so the order of the books is important, right? And this happens with a permutation. So let's just take this. We did one earlier. We had, say, 10 digits, right? And we were getting a code number with 4 digits. And so we counted that if you can't repeat them, that's one of the things I didn't put here, but with a permutation, no repeats. And so do you remember what we got when we did this calculation? It was 10 times 9 times 8 times 7. And that gave us 5,040. Another way we could think of this is as a permutation is that we've got 10 items, right? We start off, we had 10 digits, but you can't repeat them. And we're doing a permutation because the order of the code is important. You change the order, it's different. and we're going to choose 4 items. We're choosing a 4 code 4. If we had 8, we would choose 8. Well, that on your calculators, the TI-84, you'll go to your math button, and then notice here, over here, there's a probability section. So we go over to probabilities, and then the 2 we're going to be using is NPR, which is permutation, order is important. We'll see the other one is a similar type calculation, but the order is not important. So a lot of lottery programs, as long as you choose the right numbers, it doesn't matter what order you choose them in. So that would be a combination. We'll talk about that. So I do NPR, I hit enter, and it asks me to put, now if you sometimes if you have the older system, you have to actually put the number in first. So let me clear that out. You would put in 10, you would go to math, over to probability, down to permutation, and then it's got 10p, and then you put how many you're choosing, how many spaces, 4. And we're going to see we get that same number. So the calculations it's doing is 10 times 9 times 8 times 7. So that's kind of a standard thing that happens with permutations. Any questions on using the calculator to get a permutation? Okay. Yes, sir. Okay. So you whatever you're starting with. So I would do 10, math, NPR, enter, and then the last number you enter is how many we're going to choose from that group. And in this case, we're choosing 4, but the problem will tell you how many you're going to choose out of that, how many things we're arranging, and then you get your number. This is how many. And again, we need this typically to figure out what our sample space is, right? That was how many possible codes do we have, and then we could, what is the probability of getting an even code or something like that, okay? So that's that. Now, if order is not important, so you're going to read through, that's like we're selecting, it'll become evident as we go through things, and if it's not, we'll talk about that. But that's a similar type calculations. Let's say we had 10 things. We're doing a lottery. We just needed to choose the 10 numbers, but the order is now not important. And we just go over, same deal, but we use a combination instead of a permutation. Permutation is order, combination is order is not really important. Which one do you think is going to be bigger, the permutation or the combination? Permutation is going to be bigger because if you have the numbers 1, 2, 3, if order is not important, that's the same thing as 3, 2, 1 or 2, 1, 3. So notice the order you get, those same numbers can be you would count a lot of different things because when order is important. When order is not important, 1, 2, 3 is just one thing. 1, 2, 3 is the same thing as 3, 2, 1, it's the same as 2, 1, 3, and all those. So yeah, permutations are always going to be bigger. So again, part of this is just then when we go through our homework and our problems, we're looking, is order important in this? And is there an ordering? And we'll talk about that later. How are we doing so far? Okay, we're doing okay. So that is the balance of 3.1. We'll see how far we get today on 3.2, which is, let me change this a little. Let's go with, there we go. Okay, so now this is conditional probability. What it means is we have knowledge of something that has already happened, and then so it's changing the probability. So just if we didn't know anything about the weather, there might be a probability for getting in an accident and not getting in an accident, right? And then those might change depending upon the weather. It's raining, or maybe more likely. So I don't know about you. Like I said, I'm always more careful when it's raining. In fact, I was taking the curve a little like I usually do, and I said, oh, I better slow down today. Okay, so this is the definition of conditional probability. It's the probability of that event occurring, and you're going to see this. Let me back it up. You're going to see this quite a bit. This word given, that another event has already happened. And so the math notation, which again, sometimes just the symbols they use in math can be scary. And I know this because I went back after 13 years. I went back to work on my master's to get recertified to teach. And I tell you what, after being out of this for 13 years, there's all these weird symbols. And I was just, I quit my job and I said, man, I quit my job and now I don't even understand this stuff. Someone sat me down, oh, this just means this means that. So you just translate it. So what does this little bar means? It just means this, what this whole thing is, probability that event happens. This bar is the given. It's a straight bar given that A has already happened. Okay. So typically we're given information about just in general, this is the probability of A, the probability of B, but things will change if we know that A happened. Sometimes if A happened, B can't happen. Sometimes B is going to be more likely to happen. So anyway, so far so good? Okay, so let's go through some examples of how this might happen. Two cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Okay. So probabilities, okay? So how would we calculate the well, I forgot to take out the answer, but anyway. So we know that the first card was a king. We don't have to calculate any probabilities on that. We were told it's a king. So that there's, I mean, it's 100%, right? So the second card, and I guess what we could do is getting a king here is 100%. So we'll multiply that times 1. Because typically if we've got two things going on, we'd use the multiplication rule. So what would be the probability of getting a queen? Well, how many queens are in a deck of cards? 4 queens. How many cards are there in the deck now that the king has been taken out? 51. So it's a slight change, but that's the probabilities have changed because something has happened. A card was taken out and not put back. Okay. Now, if they put it back, if it was replacement, then that's a different story. It still would have been 4 out of 52. But and so then we've got 1, which is the probability that we told happened is 100%. They did draw a king, and so this is drawing the queen. Notice it's 4 out of 51, not 4 out of 52. Okay. Slight difference, but and if you look at it as a percentage, it probably wouldn't change very much, but it changes enough to get the distance. So it's about 7.8%. 4 out of 52 would be even less likely than that. Okay, does that make sense? So conditional, and actually with conditionals, a lot of times you don't even have to worry about the first thing because they already told you it happened. It's always, that means that 100% it happened. Okay. There we go. Oh, shoot. These are supposed to, well, I'm going to have to work on my slideshow for the next one. I got all the answers there. But so we could talk about why those answers work, right? So we've got this result in which 970 adults were asked whether they have ever ridden as a passenger in a self-driving vehicle. So find the probability that an adult is 18 to 64 years old, given that the adult has ridden as a passenger in a self-driving vehicle. So with the given, what part of the table are we looking at? Have you ever ridden as a passenger vehicle, a passenger self-driving vehicle? Yes or no? So which of those columns are we looking at? The yes, because that's what they told us. This person that we chose, we know they're in this column which means we don't care about this or even this because that didn't happen, right? So that's all a conditional probability. It focuses, we know this happens, so the numbers are going to change. So how would we calculate it? Well, they're 18 to 64. There's 202 out of 225. Notice we're not using this total of 970 because we've got special information. We know that we're only in this place where there's 225. And so they do the calculation now, which would be different if it was just all randomness. 18 to 64 total without knowing that would have been 751 out of 970. Okay. So you see the calculation of the probability itself really didn't change, but the way we counted changed. And we had to follow through. And again, they might have listed this as the probability that they're in the 8, probability that they're 18 to 64 group, given that they are a yes, right? So maybe that's a symbol. So we know they wrote. Making sense so far? And most of the time when you see a table and it's a conditional probability, how do we know it's conditional? What word do we look for? Look for that word given. Sometimes they go, but they're telling us something happened. So we're just saying, okay, we're going to ignore part of this table. We're only going to pay attention to the part that we were given. Okay. Now what happens is there's something called independent events. And what do you think is the difference between an independent event and a dependent event? Okay, so do you think our weather pattern here depends much on the weather in Hawaii? Maybe it might get here someday, but it's certainly not. But do you think our weather might be impacted by the weather in LA? Yeah, if it's raining there, it's probably going to be raining here, just like, yeah, it's actually raining heavier there. But so because we're close enough, our proximity, our weather is dependent upon what's going on right around the coast of California, because that's going to affect us. But what's going on in the coast of Hawaii probably is not going to make any effect. Maybe 5 days down the road or something, but it's certainly not going to affect us today. So we would say our probabilities for our weather are independent from the probabilities in Hawaii, but they are dependent. They're connected to weather in LA or weather in San Francisco or something. Okay, and what happens is that if they're independent, notice doesn't this make sense? That the probability of B happening, given that A happened, doesn't change. Probability of B is still going to be B. It doesn't matter whether A happened or didn't, because they're independent. Same thing here. Probability that A happens, given that B happens, doesn't change anything because they're completely independent. I don't care whether it's raining in Hawaii or not. That's not going to affect us here. I don't care if it's sunny in Hawaii. It's not going to affect us here. So the probabilities will not change. But if they are dependent upon each other, what ends up happening is they do change. I forgot. Should have been. They're dependent. So we're going to take a look at a couple. Again, in probability, we use cards a lot. So we'll see. Decide whether the events are independent or dependent. Selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. Just did that one. Are those dependent or independent? Dependent or independent? Independent. Does the probability change because the first one happened? Is that? They're actually dependent. Now, it's not directly just because you got a king that doesn't mean you're going to get a queen, but it changed the probability. Let's put it. Remember, the probability that the second one's a queen, if we didn't take out the king, if we hadn't replaced it, or if we would have replaced it, remember the probability of getting a queen by itself is going to be 4 out of 52. But the probability of getting a queen, given that we got a king, or actually any other card that was not replaced, was 4 out of 51. Okay, so the probabilities changed, which means for probabilities, they are dependent. Okay, solution that, where's the second? So they're dependent because the probability changed. So part of it is you got to say it's not necessarily that one's causing the other or something, but that because one thing happened, the other's probability changed. Okay, how about this one? The tossing a coin and getting a head, and then rolling a 6-sided die and obtaining a 6. Will the first one, getting a heads, change the number we could get with a die? They're separate, right? Good. So this is the probability stayed the same. Probably getting a heads or tail. So the probability of A is 1/2. Probability of B is 1/6. And the probability that A happened, that this is always kind of backwards, that probability that we get B given that A happened. Did I get this right? Sometimes I get these backwards too. Is still A happened is still 1/6. Let me just see. I don't want to get you too far off, and I've got to remember the order on these things. Oh, yeah, I'm getting it backwards. Yeah, the given goes here. The queen should go here. And what I was saying, so that you get a B given that A happened. Okay, so that line means the given. So the probabilities don't change, so they're independent. Okay. And the reason this is important is because down the road we're going to get some problems, and if the probabilities don't change, then we have a conditional, we can calculate it. So how about this one? Driving over 85 miles per hour and then getting in a car accident. Do you think those are going to be independent of each other? Think they're dependent? You could kind of, yeah, my brother would say they're independent. He says, I drive better when I go fast. I said, oh, I just don't need the car. But typically, statistics show there's faster speed, less reaction time, so more accidents. But the only way to know that is to know those facts, right? It's kind of a somewhat, I would say, subjective, but we would say these are dependent because driving faster, although sometimes driving slower, right? You got that old guy like me who's driving too slow, right? You could cause accidents too. I always drive slow when I'm in a place I don't know because, until you get to know it, and then you get going faster. So, by the way, since you guys are like on some of these farm roads, they don't have any speed limits posted. So I'm 55. Yeah, that's what I figured. But then some people are right on my tail and they want to go like 90. Yeah, I was going, whoa. So what can I do here without, getting a ticket or getting in trouble with people? So 55, but people go 65 or 70 or whatever they want. Okay. Yeah, I kind of just let them go and don't rush me. Yeah, that's the one thing when you're driving, don't get in a hurry. That's when accidents really do happen because you're pushing yourself, right? Keep yourself comfortable. All right. So here's the thing that's behind independent or not dependent. So, and sometimes we have to do a calculation to figure it out, but Here's the thing. If there's a multiplication rule for probability of A and B, the probability of A and B happening is the probability of A times the probability of B given that A already happened, right? So this is an and probability, both of these will happen. Does that make sense? That first sort of like probability that we got this, and then the second one is the probability that that second thing happened given that the first one already happened. Now, if they're independent, notice this simplifies to simply the probability of A times the probability of B. So this is where it's helpful. Sometimes in the problem, they will give you the information, the conditional, that these are independent. And if you know they're independent, we can use this formula. We just take the two probabilities they gave us and multiply them. However, if they are dependent, we've got to be sure we're using this one. Okay, so independent means we've got a simpler formula. The dependent means we may have to figure out what this conditional is. Okay, and again, I've seen the problems come at us in various ways. Sometimes they ask us whether it's independent or dependent, and they give us enough facts to do the math computations. Sometimes they tell us these events are independent, and then they want us to do the calculation. We've got to decide which one to use. And if we know if they're independent, we've got a simple formula. Otherwise, we've got a more complicated one. Is that kind of making sense? Okay. And again, this one, if A happens, this is going to change. So we have to, it's like getting that queen the second time. The deck has changed. Probabilities have changed. Okay, so let's look at an example here. 51. Thank you. Okay, so we got time. Thanks. And Friday, test corrections, and then start into the homework as you get through there. So we have a form for you. I'm not going to be here because it's a holiday for the college, but you're in good hands. And again, just to let you know, the rules, it's okay to do basically anything as long as you understand what those are. Okay. And those of you who just finished, I'll do my best to get them graded tonight, and I'll email you a scan so that they can engage that way. They'll have something different to, okay. We good so far? Okay, so let's look at this one. Two cars are selected without replacement. So without replacement, is that second one going to be dependent or independent? Dependent, right? Because the probabilities are going to change. Find the probability of selecting a king and then selecting a queen. Is this a conditional probability? What word needs to be there if this is conditional? Given. Do you see the word given? No, we don't. So this is not a conditional. It's simply saying we're going to select a king and then select a queen. Okay. So this is the probability of a king. This is the probability of a queen given that a king has already been chosen. So what's the probability of getting a king out of a general deck of cards? 4 out of 52, or 1 out of 13 if you're reducing real quick. I always like to do the count. Okay. Now, what's the probability of getting a queen given that we got a king and didn't replace it? 4 over 51. Good. And this is the multiplication rule, so we multiply them. We get 16 over a big number. Somebody can help me with what that big number is. 51 times 52. 2,652. And then you could turn it to a decimal if you'd like, percentage, but So we good with that? So that's and that, remember, it's not a conditional, but it's showing us what's happening with this multiplication rule. Okay. And it was dependent. A coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. Yeah, kind of the same thing we did, right? Is this dependent or independent? This one is independent because they're not going to change probabilities. They don't affect each other. Probability tossing a heads, 1/2. Probability getting a 6, there's 1/6 on the die out of 6 possibilities, 1/6. And the multiplication rule says we multiply them. And thus, these are independent events, and we get 1/12. Okay. And we could do this, I think we did this maybe with a tree diagram before where we could count them. And we start seeing the match between the counting and the theories. Okay. Still got 4 minutes. I'll give you a couple extra minutes. We'll get done here. Almost done. Okay. And they're independent. Okay. Maybe turn this down. I'm not going to say the words. I'll just say ACL. You know what an ACL is? If you're an athlete, yeah, it's some ligament thing that you tear, and it's not real good, right? Reconstructive surgery, the probability that surgery is successful is 95%. That's pretty good. Find the probability that 3 ACL surgeries are successful. I don't know if that they're necessarily on the same person, but if we have 3 in a row, what would be the probability that the first one is successful? 95% or 0.095. How about the second one? Same. We would think these would be independent. They don't give us enough information. I guess we just got 3 of them. But if in general it's 95%, we would assume that the next one would be 95. No. Now, earlier I was thinking maybe these were all on the same person. You had to have it done 3 times. And then I thought, well, maybe by the 3rd time you just better stop playing that sport, right? But I read it today and I said, oh, they don't say it's on the same person. For all 3 of them to be successful, we multiply all these together, and what do we get? Zero point what? 85. Okay, so 85%. That all 3 would be successful. It doesn't sound as good. I mean, you see 95%, yeah, you got a really good chance in each individually, but to have 3 done in a row, it's an 85% chance. Okay. Now, remember, this is kind of getting us back to the beginning, so I'll stop with this one. But find the probability that none of the 3 would be successful. So what did we just find? That all of them being successful, we could subtract it off. Well, that we're going to have 3. So the last one, all 3 together, we came up 85%, I think, right? So it was 85% that all 3 would be successful. So the probability that none are successful, isn't that the complement? You're either all successful or none are successful. I'm not sure. Let's see.
Well, we have 1 successful, 2 successful. 3
We could.
So it could be the complement.
Can't quite be the complement, but what's the probability that it's not successful? 5%. And that brings us to the end of the class. 0.05, yeah. We'll say by the bell. We'll see you next week.
Bye, you guys. See you tomorrow.